Okay, hello everyone. Welcome back for part 3 of chapter 14. Here we're going to talk just a little bit about how to calculate concentrations of these H3O plus hydronium ions and OH minus hydroxide ions in solution, the things that are going to kind of make it acidic or basic. From there, we're going to talk about scales that we use to measure the amount of those ions, like pH and pOH. And then once we know about those scales, we'll be able to go back and forth between pH, concentration of H3O plus, concentration of H3O plus, back to pOH, or pH, pOH to concentration of OH minus, and concentration of OH minus to pOH. And then from there are some relationships between pH and pOH that allow us to move between both scales pretty seamlessly. So let's go ahead and get into it. Okay, so hydrangeas are litmus paper? What? Well, we've seen in the lab that litmus paper can change color in an acidic or a basic environment. We've also seen in our titration lab that indicators like phenolphthalein will change color. It's clear in an acidic environment and pink in a basic environment. Well, what other things we might have experienced that change color with pH? Well, woo! It's hydrangeas. So for a long time, my parents had the most beautiful hydrangea plant in our backyard. It was this wonderful lavender blue color. It looked just like this one up here. However, hydrangeas actually can have different colors of flowers based upon the pH of the soil or the acidity or basicity of the soil. So, hydrangeas are blue or lavender in a acidic soil. So, our soil in my backyard must be just a bit acidic. So, we always had those lovely purple-blue flowers. However, if you have a basic environment, you'll have pinks or reds in your flowers instead. So, just like the phenolphthalein turned pink, they go ahead and they turn pink in a basic soil as well. So, depending upon the color of your hydrangeas, you can kind of use them as a bit of a litmus paper for your soil to determine how acidic or how basic your soil is based upon the color that you see of your flowers. So, let's talk a little bit more about what I mean by pH and how we can measure how acidic or basic something is. So, we know water is amphoteric, so remember, amphoteric means it can act as an acid or act as a base. So we can actually leverage this information to think about how acidic or basic a solution is. So water kind of acts as an acid and a base with itself all the time. I don't know why, I think this is one of the coolest things I learned. So water is constantly going back and forwards through reactions where it's as H2O or it reacts with itself to become H3O plus and OH minus. So you might have two water molecules that pass one of their protons between them and go back and forth between being a water molecule or being H3O plus and OH minus. Two water molecules, H3O plus, OH minus, back and forth, passing that proton throughout the solution. So water isn't technically just pure H2O. It's going back and forth with this reaction of H3O plus and OH minus as well. So when we add an acid or a base to a sample of water, we either increase the concentration of H3O plus, those protons, or we increase the amount of OH minus with bases. So acids increase H3O plus, bases increase OH minus. Well, if we can measure that amount of H3O plus in solution, and if it's more than what we expect for water, well then boom, we have an acid. Or if we have something that has more OH minus than we would expect in water, boom, we have a base, for example. So, in this chapter, we need to talk just a little teeny tiny bit about a cool little piece of notation we're going to use. We're going to use these square brackets to denote a molar concentration in this chapter. So, for example, we've been using that capital M to mean moles divided by liters. However, in this chapter, we're going to use square brackets to mean the same thing. I'll talk to you a little bit later on about why this occurs and why we choose to use this when talking about pH, for example. But the square brackets are just another way to talk about molar concentration. So if you see square brackets around something like H3O plus written like this, or OH minus written like this, that means we're talking about a molar concentration, how many moles per liter we have. So if you see those square brackets, you should assume that the unit is capital M, molarity, molar, moles divided by liters. So that being said, water has an exactly equal balance of the concentration of H3O plus equals the concentration of OH minus, and that's going to be 1.0 times 10 to the negative 7th, and we can assume that capital M molar unit is back there. So I might say the concentration of H3O plus is equal to the concentration of OH minus, which is 1.0 times 10 to the minus 7 molar. So we figured this out through experimentation, and we know that those molarities are equal. So if we know that the concentration of OH minus and the concentration of H3O plus are exactly equal, and they are each 1.0 times 10 to the minus 7th, we can calculate what we call the Kw, or the ion product constant for water. So this way it gives us a ratio so that we can compare how much H3O plus or how much OH minus is in a given solution, and it kind of jumps off from that base point of what water kind of should be or originally is, and what happens to each value as we change the concentration of OH minus or we change the concentration of H3O plus, for example. So to calculate Kw, or that ion product constant for water, we just multiply the concentration of H3O plus times the concentration of OH minus to get that value. So we know that the concentration of each of those in water is 1.0 times 10 to the minus 7. So if I multiply those two together, I get 1.0 times 10 to the minus 14. So in water, for example, we would expect Kw to equal the concentration of H3O plus times the concentration of OH minus, and that is going to, in the end, equal 1.0 times 10 to the minus 14. So hypothetically, if I put an acid into solution, it's going to create those H3O plus ions like we talked about in our previous definitions of acids. They're going to either increase the number of protons, which react with water to create H3O plus, or they're going to react with water to create more H3O plus. So you have a scenario here where you've increased this concentration. So if you increase this concentration of H3O plus, it's going to be greater than the concentration of OH minus. So we can kind of use this ratio, I'll show you how in a minute, to determine these concentrations if we have one or the other. So if you have an acidic solution, your concentration of H3O plus is greater than your concentration of OH minus. When you have a basic solution, you have a concentration of OH minus that is greater than that of the concentration of H3O plus. And when you have a neutral solution that is neither acidic nor basic, your concentration of H3O plus equals your concentration of OH minus, just like up here in water, as we expect. Water is a neutral compound with a pH of 7. We'll talk about it. But it sits right here in the center of our graph. So, for example, if we have something that's very acidic, we're going to see the concentration of H3O plus be quite large. Remember, we have negative exponents, so the smaller like the value of the number, the bigger it is, versus down here, this has a bigger value of 14, so this is going to be a very small number. So really big numbers over here, really small numbers over here in comparison. So if I have something that's really acidic, I'm going to have a high concentration of H3O+, but that means I tend to have a low concentration of OH-. Over here, if I have a low concentration of H3O+, I have a high concentration of OH-, and that's a basic environment, for example. So as I've mentioned before, an acid and base, that kind of definition, it's not just a binary, it's on a scale. So I'm kind of looking how acidic is something versus how basic is something, and they're just opposite ends of a number line almost. So if I'm looking here, as I increase how acidic something is, if I increase how acidic something is, that means it's getting less basic, and if I increase how basic something is, it's getting much less acidic. So as I increase H3O+, I'm decreasing my concentration of OH-. As I'm increasing my concentration of OH-, I'm decreasing my concentration of H3O+, and that is reflected here in our Kw equation. So, okay, so I'm going to go ahead and work through a couple examples here of how we can use that information contained from that ionization product of water to figure out how concentration changes of H3O+ here, for example, when we change the concentration of OH- and vice versa. So our first example here says if a solution has a hydroxide concentration of OH- equals 3.7 minus 10 times 10 to the minus 6th, what is the concentration of H3O+ in this solution? So we're going to go ahead and use that Kw equation in this case to figure out how that H3O+ concentration is changed since we have a higher concentration of OH- in our solution rather than what we would have expected for pure water being 1.0 times 10 to the minus 7th. So that being said, our equation is Kw equals the concentration of H3O+ times the concentration of OH- equals 1.0 times 10 to the minus 14. So what I want you guys to remember here about this equation is that with Kw, it's not actually a variable. We already know what it equals. It equals that 1.0 times 10 to the minus 14. So when we're plugging into our equation, we're not worried about filling that value. So if I go back into my equation, it looks like I'm given 3.7 times 10 to the minus 6, and that's the concentration of OH-. And what I'm looking for, what I need, is actually to find that concentration of H3O+, which, given our equation here, we can very clearly do that with. So I'm going to go ahead and plug in my value for OH- and solve for H3O+. So I have the concentration of H3O+. I'm going to leave that alone. I don't know what it is. It's what I'm looking for. I'm going to multiply that by 3.7 times 10 to the minus 6. And I'm going to go ahead and say that equals 1.0 times 10 to the minus 14. So now I just need to solve for my concentration of H3O+. So I'm going to go ahead and I'm going to divide both sides here by 3.7 times 10 to the minus 6, 3.7 times 10 to the minus 6, and that leaves me with my concentration of H3O+ equals 2.702702703 times 10 to the minus 9. And of course here our brackets mean that we've assumed its molarity. We're not worried about tacking on those units at the end at this point. So what we really need to look for are sig figs. If I go back to my original problem, I'm given 3.7 times 10 to the minus 6, and 3.7 has 2 sig figs. So my answer gets 2 sig figs. So my answer is H3O+ concentration equals 2.7 times 10 to the minus 9. So this here is my final answer. And because I've written it with square brackets around the H3O+, I can assume that my concentration is 2.7 times 10 to the minus 9 molar. I just don't have to write the M because I've already told you with the brackets. So we want to know if this solution is acidic or basic. Well, we can either look at the concentration of H3O+, look at the concentration of OH-, what we see is that we would expect each of those to be equal to each other in a perfectly neutral solution. So we would have H3O plus equals 1.0 times 10 to the minus 7, OH minus equals 1.0 times 10 to the minus 7. However, that's not really the case that we have here. We see that we have 3.7 times 10 to the minus 6 as our value for OH minus, and that's actually a greater number than 1.0 times 10 to the minus 7. Remember, we're comparing negative exponents, so times 10 to the minus 6 is a bigger number than times 10 to the minus 7. So if we have more OH minus and we look at our concentration of H3O plus, well, 10 to the minus 9 is less than 10 to the minus 7. So that means we have less concentration of H3O plus than we do of concentration of OH minus. So that means we have a basic solution in this case. So our solution is basic. Okay, let's go ahead and do the second example for these set of KW problems. However, there is one thing that I want to point out in the slides here. For each of these different calculation problems, except for when we're doing basic addition and subtraction, I have included a screen capture of my calculator so you can see how I typed it into my calculator, how I got my answer. So you can see where I used parentheses in each of these problems as well. So let's go ahead and do example number 2 as well. So example number 2 says if a solution has a hydronium concentration of H3O plus equals 1.1 times 10 to the minus 7, what is the concentration of OH minus in this solution? Is the solution acidic or basic? So let's go ahead. It looks like here I'm going to use that KW equation again because I'm comparing concentrations of H3O plus and OH minus. So my equation is going to be concentration of H3O plus times the concentration of OH minus equals 1.0 times 10 to the minus 14. Remembering that KW is not a variable we're plugging in for, it looks like I should be able to solve this equation as I am given that I have a concentration of H3O plus that equals 1.1 times 10 to the minus 7. And I'm looking for my concentration of OH minus. So I can go ahead and solve this problem. So in this case, I'm going to go ahead and plug my value in for H3O plus. So that's going to be 1.1 times 10 to the minus 7 times that concentration of OH minus that we're looking for, and that's going to equal 1.0 times 10 to the minus 14. So we can go ahead and divide both sides by that value of 1.1 times 10 to the minus 7, 1.1 times 10 to the minus 7, and we get that our concentration of OH minus equals 9.0909090909, so on and so forth, times 10 to the minus 8. So our concentration of OH minus equals, in the proper sig figs, I have 2 sig figs here, so 9.1 times 10 to the minus 8 is my final answer. And again, that's in molarity because I have those brackets of OH minus, or around OH minus, so I know that that is going to be molarity. So in this case, I have just a few more H3O plus ions than I would expect in water because I would expect water to be 1.1 or 1.0 times 10 to the minus 7th. Here I have 1.1 times 10 to the minus 7th, so I have more H3O plus than I expect. And if I look at that value I got for OH minus, my 10 to the minus 8 is less than 10 to the minus 7, so I have less OH minus than I would expect. So this solution is going to be acidic because I have more H3O plus than I do OH minus, for example. So go ahead, make sure you check out the slides where you can see where I have typed it in my calculator for you as well. And then I've given you some practice problems to work through as well. So go ahead and check that out. And we're going to begin talking about the pH scale. we want to think about this thing called the pH scale. I've been saying these words, but what have I been hinting at this whole time? Well, we can talk about how relatively acidic or basic something is in looking at that concentration of H3O plus versus a concentration of OH minus. However, when we're looking at these concentrations, they tend to be very small. They're usually less than 1, and we kind of have these, so we end up with these weird numbers that we keep in scientific notation to try to keep track of them. But then I'm comparing things like 10 to the minus 6 to 10 to the minus 8. And I kind of tend to get that stuff mixed up all the time. Which one's bigger, which one's smaller. So basically, we know that chemists don't like to be messy. We don't like to deal with this stuff. As much as we develop scientific notation to take away some of the mess, we've developed the pH scale to take away the mess of using scientific notation when comparing really, really small numbers, so that we don't have to try to figure out, all right, 10 to the minus 6 is bigger number than 10 to the minus 8, for example. So of course, we developed a specific scale to measure the acidity or basicity of or basicity based on the amount of H3O plus. So if we just look at the concentration of H3O plus, we can call this pH in a scale. So we'll talk about how we calculate between pH and H3O plus and kind of where this scale came from a little bit later in this lecture, but for right now, we're just going to think about the fact that pH measures that concentration of H3O plus. So pH measures the concentration of H3O plus, and it kind of makes it a little bit easier of a scale to compare than if we're trying to compare very, very small numbers, for example. So this scale runs from 1 to 14. So if something has a very low pH, it's going to be acidic, and if something has a very high pH, it's going to be basic. So exactly, pH 7 is neutral, so that's where our balance of H3O plus equals our balance of OH minus. And so at pH 7, that's neutral. That's going to be water in our case. If you have a pH that is less than 7, so anything less than 7 is going to be acidic. Anything greater than 7 is going to be basic. So 7 is our neutral land. Anything less than 7 is acidic. Anything greater than 7 is basic, because that's basically saying down here we have a really high concentration of H3O plus. And then if we're in a land that's greater than 7, we're saying we have a very small concentration of H3O plus. Which means our concentration of H3O or OH minus is very high, so it's more basic. So it's the same thing. We're still comparing the same thing that we saw in this picture here, where we have these amounts of H3O plus that are very small, going all the way up to that basic environment where we have, or very large to where we have a basic environment where our concentration of H3O plus is very small. So, and they're exact opposites. So, again, pH, if you have something that has a pH of 7, it's neutral. If you have something that has a pH of less than 7, it's acidic. If you have a pH of something that's greater than 7, it's going to be basic. So, let's run through some quick practice examples of things that are acidic and basic. So, a can of pop, my Mountain Dew from 7-Eleven this morning. A pH of pop is around 3.0. Is this going to be acidic or basic? Go ahead, submit your guesses in your head. That's going to be acidic. If the pH is less than 7, it's acidic. So 3 is less than 7, it's acidic. The pH of milk of magnesia is around 10.5. Is it acidic or basic? Think about it in your head. Submit your answer. 3, 2, 1. Well, it's going to be basic. That pH is greater than 7. So anything greater than 7 is basic. Anything less than 7 is acidic. So milk of magnesia is about 10.5. So it's basic. That's also something you might take to settle your stomach in some cases as well, in very small amounts. It's another base there on our list. Let's go ahead and think about the pH of egg whites. So the pH of egg whites is approximately 8.0. Is this acidic or basic? Think about it in your head, settle on your final answer. If it has, a pH greater than 7, it's going to be considered basic. So this scale is also relative in terms of the fact that egg whites are a little less basic quality than milk of magnesia is. So anything closer to 14 is more of a strong base. Anything kind of closer to 7 but still above 7 is going to be a weaker base. And then same thing happens with the acids. So if it has a super low pH of like 1, of 2, of 3, that's going to be pretty acidic. Whereas a pH of like 5 or 6 is less acidic. It's weak. It's more weak in its acid characteristics. So this scale also is relative. So again, egg whites are a bit less basic than milk of magnesia is. And finally, the pH of water is around 7. Is it acidic or is it basic? Is water acidic or basic on the pH scale? We know by definition it can be both, but remember, pH of 7 is a neutral compound. It's neither acidic nor basic. If it sits around pH of 7, it's a neutral compound, neither acidic nor basic. So those are just some quick run-throughs of things that are acidic or basic. So again, we're just comparing it to that number 7. If the number is greater than 7, it's basic. If the number is 7, it's neutral. If the number is less than 7, it is acidic. So, as I mentioned before, as we're kind of introducing ourselves into this pH scale, and we're calculating pH, and we want to maybe calculate our pH, because that pH scale is based on the concentration of H3O+, we can use the amount of H3O+ to calculate the pH. Again, we can use, or we can go backwards, and we can also use the pH to calculate the concentration of H3O+ in solution as well. So what's been quietly hidden underneath what I have been saying is that actual relationship between pH and that concentration of H3O+. So pH is what we call a logarithmic scale. We're going to talk just a little bit about math here in a very big way, in a very broad way. So don't run, please stick with me. Let's just think about this. So when I'm talking about a logarithmic scale, what I mean is for every one, like if you increase pH by 1, so I'm going to go from a pH of 1 to a pH of 2, or let's say I'm going from a pH of 2 to a pH of 1. As that pH changes, I'm changing by a factor of 10, basically. So if I am saying that I'm going like between those characteristics, that's changing the exponent. So it's not changing the front value of our scientific notation. If I'm increasing my pH or increasing that number, it's going to change that exponent on our 10 to the minus whatever, because that is what is denoting that large amount of concentration. So realistically, when we're looking at our pH scale, it's kind of like this is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, so on and so forth. So really that's kind of what's hiding underneath your pH is we're able to kind of basically say, all right, if something's 10 to the minus 1, it's in this range of pH of 1, and we can do a little bit of math with the logarithmic function so that we can find out exactly the difference between those ones that are 10 to the minus 1, for example. The way we do this is using this pH equation here. So you don't have to know what a logarithmic function is. You don't have to know what it looks like. All you need to know is that it changes that exponent if we change the pH, and this is the relationship between the two. So therefore, in these relationships, all I'm asking is that you know how to type minus log into your calculator, okay? And to type 10 to the minus whatever into your calculator. So, for example, pH equals 10 to the minus log of the concentration of H3O+. So you'll have to type a negative in, and you'll have a log value. you'll be able to calculate the log value of that concentration of H3O plus. So here I have the concentration of H3O plus. I'm not going to talk about the mathematics behind this. If you want to see the mathematics behind this, it's in your textbook. You can go ahead and read that in your chapter. But to undo the logarithmic function, we can go ahead and say H3O plus equals 10 to the minus pH. So that's 10 to the negative of whatever the pH is. So we got to kind of flip some negative signs into this based upon our negative exponent. But what I just want to be clear here is you don't actually have to be in-depth mathematically concerned about what the logarithmic function is. You just got to be able to find the logarithmic button on your calculator. So pH equals minus log of the concentration of H3O plus, and the concentration of H3O plus equals 10 to the minus pH. So let's go ahead and do some examples so I can show you what I expect, and then you can also see on the screen in the slides how I type that into my calculator, so you can have some practice typing in that minus log or 10 to the minus whatever as well. Okay, so we're going to go ahead, we're going to work through a couple examples of how we can go between pH and the concentration of H3O plus and back and forth vice versa. So our first example here says, what is the pH of a solution with an H3O plus concentration equal to 5.4 times 10 to the minus 7, for example. So we're going to go ahead and figure out what we're given. Here we are given that the concentration of H3O plus equals 5.4 times 10 to the minus 7. And what we're looking for, it's asking us what is the pH. So if I kind of see that I'm thinking about pH here, I have a concentration of H3O plus. I can go ahead and use that equation that says pH equals minus log times the minus log of the concentration of H3O plus. So it looks like here I have the variables that I'm looking for. This is going to help me to calculate pH here, and I'm given that value that I'm going to go ahead and plug it in. So I can say that pH equals minus log of 5.4 times 10 to the minus 7, that concentration of H3O plus, so that then I can say that the pH equals 6.26760,624. And then if I want to triple check that I've gotten back to the correct sig figs, up here I have 5.4 has 2 sig figs, so I'm going to go ahead and I'm going to round this to 2 sig figs. There are technically more complicated sig fig rules that underlie this, but in this class we're just going to leave our sig fig rules the way that they are. However, you may experience a more stringent set of sig fig rules when it comes to using logarithmic functions and calculating pH, but we're going to leave it where we've put it for now with the sig figs. I think we'll be okay. So my answer here, my final answer, is going to be 6.3 is my pH. So one thing I want to say about this too is that it's very important that you keep your minus signs correct and in the correct place when you're doing this. So if you get something that's not between that 1 and 14 scale of pH, you may have forgotten to put that negative sign up here in your 10 to the minus 7th when you're typing it in your calculator. Sometimes that can be an easy mistake to make, as well as forgetting this negative out front of the log. That negative out front of the log as well. If you get a negative number when you're calculating your pH, it's probably because you forgot to type that negative log into your calculator. So that is how, if you're given the concentration of H3O plus, you can go ahead and find the pH. And if you want to see how I'm typing that into my calculator, make sure you go ahead, you check the slides, and you can see that picture I put of my calculator screen into the slides. So let's go ahead and do another example here of going between pH and the concentration of H3O plus. So here, it's saying, what is the concentration of H3O plus in a solution with a pH of 12? So before we were given the concentration of H3O plus, we were looking for the pH. Now we're given the pH. How do we go back to that concentration of H3O+? So here I am again given that pH equals 12.6. And it says, what is the concentration of H3O+? So that means H3O+ is what I'm looking for. We do have an equation that relates concentration of H3O+ to pH. Technically, if you know how to work logarithms, you can do the math and only use one equation for all of this. However, I have done the math. I have solved the equation for you. The book shows you the math. They've solved the equation for you as well. So the equation that we use to relate the concentration of H3O+ when given the pH is that concentration of H3O+ equals 10 to the minus pH. So you want to use that first equation that we just saw, pH equals negative log of the concentration of H3O+, if you're looking for pH. Here, if you're looking for the concentration of H3O+, you should be using this equation. Concentration of H3O+ equals 10 to the minus pH. So let's go ahead and plug in and solve. Concentration of H3O+ equals 10 to the minus pH. Well, here my pH is 12.6, so I'd say that's 10 to the minus 12.6. Pretty straightforward. So then I eventually see that my concentration of H3O+ equals 2.51188643 times 10 to the minus 13. And the concentration of H3O+ rounded to the proper number of significant figures. Here I'm given 3 in my problem, so I'm going to go ahead and round my answer to 3 sig figs. So I would say this is 2.51 times 10 to the minus 13. And we would say that that is molarity, capital M, but again, that's covered in the fact that I have used those square brackets around that H3O+. So as you're working through these problems, you can also start to look at the pH itself and look at the concentration of H3O+ and determine if this actually makes sense in the end for what you expect in this situation. So if I have a pH of 12.6, I know that that's basic. It's greater than 7. The pH is greater than 7, so that means my solution is basic. And so I'm expecting a very, very small concentration of H3O+. Here, it's 2.51 times 10 to the minus 13. That's a very low concentration, much lower than that expected water neutral concentration of 1.0 times 10 to the minus 7. So way smaller, a very small concentration of H3O+ makes sense for a very high pH. And then it would be the exact opposite. So in the first problem as well, we saw that we have a relatively close to neutral, but a little bit less than neutral concentration of H3O+, that is 5.4 times 10 to the minus 7th. It's more than 1.0 times 10 to the minus 7th. So we're expecting to see a pH less than 7 here, simply because our concentration of H3O+ is greater than that 1.0 times 10 to the minus 7 we would expect in water, which would be a neutral compound. So it does make sense that I have a pH of 6.3 here. So you can always go back, always triple check your answers doing something like this so that you can better make sure that you are following everything in line and thinking critically about, are my answers actually okay? You can use some of the concepts given in this lecture to determine that for yourself as well. So those are just some example calculations of how we can go between pH and that concentration of H3O+, for example. I have also given you a couple more practice problems written out on the slide that you could work through yourself, as well as, again, my calculator screen so you could see how I would have typed that in. So that being said, we're going to go ahead and move on and start to talk about the opposite scale of pOH. Okay, so we have just a little bit more information here to cover about the pOH scale. So I'm wondering, have you made the connection yet? So if we have the pH scale, I wonder what the pOH scale measures. The concentration of pOH, or the concentration of OH minus instead, of course. So it's literally the exact opposite. So instead of measuring the level of acidity, which was kind of what we're measuring with pH, here we're going to be measuring the level of basicity with pOH instead. So we're kind of comparing these two different scales that are exactly opposite of each other. So again, pOH of 7 is neutral, pH of 7 is neutral. However, a very, very low pOH indicates a lot of OH minus ions in solution. So therefore, that's going to be a very basic solution. So if the pOH is less than 7, we're going to have a basic solution. And if the pOH is greater than 7, we're going to have an acidic solution. So it works just like that same scale did for pH, where we were thinking about it as a logarithmic scale. It's just, again, measuring that concentration, but it's taking away all that messiness of the scientific notation, those negative exponents. It gives us just a little bit more straightforward numbers to look at and compare, and it does that using that logarithmic function. So these two equations on your screen should look very familiar. They look just like the ones we just had. However, it's that pOH equals the negative log of the concentration of OH minus, and the concentration of OH minus equals 10 to the minus pOH. So same kind of deal here. We're going back and forth in the same way. However, instead of kind of measuring that level of H3O plus, here we're measuring the level of OH minus. So we're thinking about bases rather than acids. So let's go ahead and work through just a couple of examples. I'm going back and forth on this scale as well and kind of thinking about, do our answers make sense? So the first question here says, what is the pOH of a solution with the concentration of OH minus equal to 2.4 to the minus 8? So if I'm looking through this problem, I'm sorting through the information. What I need to do is take that what I'm given here is the concentration of OH minus equals 2.4 times 10 to the minus 8. And I need, kind of bad handwriting there. I need the pOH. It says, what is the pOH? Given that the concentration of OH minus is this. So I'm looking for pOH, and I'm given the concentration of OH minus. Well, we do have an equation that relates those two concepts together. That is that pOH equals minus log times the concentration of OH minus that hydroxide ion. So we could say that pOH equals minus log of that concentration of OH minus that we're given in our problem. So I'll go ahead, plug that in. I will say that pOH equals minus log 2.4 times 10 to the minus 8. I can go ahead and plug that into my calculator. If I do that, I get that the pOH is 7.619788758. Big number. Of course, we have to make sure that we put that in the correct number of sig figs. Here, again, 2 sig figs and 2.4. So I'm going to go ahead and say that my pOH equals 7.6. So that'll be my final answer. And just like we talked about a bit with the pH and the concentration of H3O+, we can determine here if this makes sense as well. So if I have a concentration of OH minus equals 2.4 times 10 to the minus 8th, well, 10 to the minus 8 is less than 10 to the minus 7, so that's a smaller number than that 1.0 times 10 to the minus 7 I would expect in a neutral solution. So if I have less OH minus ions, I would expect that my pOH would be greater than 7 then. So my pOH would be greater than 7 if I have a low number of OH minus ions in solution. So it's kind of the opposite. The more basic it is, the more OH minus it has in solution, the closer to 1 it is. Here we're doing the opposite. It has less OH minus ions in solution than my pH neutral 7, or my pOH neutral 7 compound would be. So I'm thinking that my answer looks like I'm in a good place because I end up with 7.6, which would indicate that it is a little bit more acidic. It has less OH minus ions in solution. So I think my answer here checks out. Okay, so let's go ahead and check out the second one as well that I have given you. It says that it wants to know if the pOH of a solution is measured to be 8.9, what is the concentration of OH minus? Well, so if the pOH in solution is measured to be 8.9, I can tell you that I'm given that pOH equals 8.9, and it's asking what is the concentration of OH minus, so I need the concentration of OH minus here. So we have an equation that relates that concentration of OH minus to a given pH value. Again, just like with pH and concentration of H3O+, we could do a bunch of complicated math and use that same equation that we used in problem 1. However, forget it. I already did it for you. Let's go ahead and choose the equation that says OH minus equals 10 to the minus pOH. So that being said, I can go ahead and start to plug in my values that I was given. So concentration of OH minus equals 10 to the minus 8.9. And then that means that the concentration of OH minus equals 1.2589,25412 times 10 to the minus 9. And then we could say that concentration of OH minus equals, we need to triple check that we have the correct number of sig figs. Here, I'm given 2 sig figs as 8.9, so I can go ahead and round this to 2 sig figs, which is going to be 1.3 times 10 to the minus 9. And of course, again, I can go back, triple check that my answer makes sense. So it's kind of the last step in every problem. Did what I get make sense? Well, if I have 1.3 times 10 to the minus 9 molar concentration of OH minus, that 10 to the minus 9 is much less than 10 to the minus 7. So that would be what we expect in a pOH 7 neutral compound. So if I have less OH minus ions, that means I can expect that my pOH is going to be very high because there are not very many of those in solution. So it's not going to be very basic, and that's reflected in a high pOH. So my pOH is greater than 7, and that is exactly what I expect if I have a concentration of OH minus that is much smaller than my concentration of what I would expect in a neutral compound. So my answers here check out, make sense, which is a good thing here for us. So again, you can always go back through the slides here, make sure you've checked it out, seen how I type that into my calculator. I've given you 2 practice problems to work through on your own as well. Again, I've given you the math for a solution once you've tried it yourself, and I do show you how to type it into your calculator as well. So go ahead and check that out. But before I leave you today, I just need to have a quick discussion with you about the relationship between pH and pOH. And so I'm not going to give you the complicated back history math discussion to lead you to this relationship. However, you can see this wonderful relationship mathed out, worked out in your textbook. So go ahead, check that out. If you want to see why this relationship occurs, the reasoning is in your textbook. However, I'm more concerned that you understand the relationship here. So because of their relationship with Kw through their connection to the concentration of H3O+ and the concentration of OH-, and how those two together make up that Kw value, what happens is that pH and pOH are exactly opposite of each other with a very clear relationship. So pH plus pOH always equals 14. So you can always go back and forth in any situation between pH and pOH, by just subtracting from 14, basically. So let's say, hypothetically, I give you a problem and it gives you a pH, but it's asking for a concentration of OH minus. Well, you could use an equation like this to very quickly flip from pH to pOH, and then use that pOH in your further equations and calculations like we just did in problem 2 that we just saw. So, that being said, again, pH plus pOH is going to equal 14. So if you have a really high pOH, you have a really low pH, which makes sense. A high pOH indicates a not very basic solution, whereas a low pH indicates a very acidic solution. So you can see that relationship at play there. If the number for pH is low, that means the number for pOH has to be high, and vice versa. So let's go ahead. I'm not going to put any math up on the screen. We can probably just talk about this very quickly here. But if I want to know what the pH of a solution with a pH of 13.1 is, I can go ahead and just very quickly do that subtraction and find that pH plus pOH equals 14. So pH plus 13.1 is going to equal 14 in my case here. So if I just subtract 13.1 from both sides, I get that my pH equals 0.9. When we're working through these problems and we're thinking about sig figs, remember here, we're now using the addition and subtraction rules. So we're counting our number of decimal points after the, or our number of places after the decimal point. So here, 13.1 has one number after the decimal point, so that means I round to one number after the decimal point, 0.9. Oftentimes, this is just going to be what you type in and see in your calculator anyways. So keep that in mind. Let's go ahead and just talk about one last example here. We want to know what is the pOH of a solution with a pH of 2.3. In your head first, you could kind of think here, do I expect it to be low or high? If I have a low pOH or pH, I expect a high pOH. So let's see if it checks out. So here I have pH plus pOH equals 14. I could say that I'm going to go ahead and plug in my pH value that I'm given, 2.3 plus pOH equals 14. I'd subtract 2.3 from both sides and make sure that my answer has one decimal place. And in the end, I get that pOH equals 11.7. So that is a little bit of information about how to go back and forth between pH and pOH. I have given you, again, a couple of practice problems just to practice flipping back and forth, going between the two so that you can see how that changes, and you can kind of practice with those sig figs as well. So that being said, that is our end of our chapter on acids and bases. So I hope you've learned just a little bit about how these compounds work in the real world and how we experience them in our everyday life. So thanks very much for the watch, and let me know if you have any questions on the homework.